Hey guys, this is a real quick video about finding points where electric field and electric potential cancel out completely. If you just need to see the electric potential part, skip to about the 8-minute mark. Thanks. When you're trying to find a point where the electric fields due to 2 point charges cancel out, the first step is figuring out approximately where they could cancel out. So if I take, that circle didn't really, there we go. If I take a 1 point charge, let's say it's a plus 2q, and over here we've got a plus 1q. If I were to, I don't know, pick a random point, somewhere on this line that runs between them, say like over here, that would be a bad guess for where the fields would cancel out. Because if you recall, fields go out away from positive charges, right? Away from them. And field lines go in towards negative charges. So that means that, this 2q over here and this q would actually both be making fields at this point, which would be going to the right, right? The plus q wants to make a field that goes away from it, and the plus 2q also wants to do the same. So over to the right, away from them, would in fact be in the same direction. So this is not canceling right there. Not canceling. I don't know if I have enough. Okay. All right. If I tried over way on the left over here somewhere, we'd get the same story. There's no way they could cancel. All right, but then somewhere in between them, in fact, they will cancel. The spot where the fields are always going to be canceling, whether you have like charges, as I picked here, or opposite charges, is always going to have to be closer to the smaller one. Okay, so let me, in red now, pick a good estimate. Because the field due to the plus q would be to the left, which is away from it. And due to the plus 2q would be to the right, because that's away from the plus 2q. And so there's some very specific spot somewhere in between these two where the fields can cancel out. All right, now the next step is we've got to define our variables. This is where drawing a diagram is actually really useful. So if you're trying to work one of these problems without drawing a diagram, then you are, for absolutely no reason, sort of crippling yourself, preventing yourself from actually working it out. So if they say the distance between them is d, all right, I can handle that. We'll call it d. That whole distance is d. Well, that means then that the distance from, let's say the plus q is, I don't know, we got to call it something if we're going to solve for it. So how about x? Well, that means that the distance from the plus 2q to that point is d minus x. All right, and now we have enough to go on for setting up our electric field calculation. All right, so the electric field due to the plus 2q would be, the equation being kq over r squared r hat would be 2kq over, all right, r from the 2q is d minus x, and then squared, because that's part of the formula. The field from the plus 2q is in the opposite direction, and it's only a 1q, and it's only x away from the point where the fields cancel. So now we can just say those two fields, whatever they each are, add up to 0. All right, from there's going to be some algebra, so I'll pause my narration and just kind of work it out, and then you can ponder that on your own time. And there you have it. All right, you can follow that through on your own time again. Now, the way the algebra went for this particular problem would be only slightly different if I had given you two opposite charges instead. So when you have two opposite charges, let's draw that over here, where you've got, let's say plus 2q and minus q, the field from these ones actually can't cancel out anywhere in between them. So remember the mental process that we went through with the 2q and the 1q, or it didn't have to be a mental, we could draw arrows, that would help. The process we went through, so you said fields go away from positives and they go towards negatives. So, everywhere around this 2q, it's making a field that goes away from it, all right? Everywhere around the minus q, it's making a field that's going towards it. So you can see that at this point, which is in between them, the field that the minus q produces would go towards it, and the field that the plus 2q would point away from it. And again, you can see that's the same direction. Those aren't subtracting and canceling, those are adding together, which was the same problem we had. Well, I didn't mean to zoom all the way out like that. It was the same problem we had right here. We said they went in the same direction, so they're not canceling out. Okay, so if the field lines that you draw go in the same direction, those fields are not canceling. All right, so that means then for the opposite charges here, the field lines have to point in opposite directions, and so therefore we're not going to pick in between the charges. We've got to pick somewhere either over to the left or over to the right. In this case, we'll pick over to the right. If you forgot the reason why, it has to do with you have to be closer to the smaller charge. If you're closer to the larger charge, the field from that one is always going to dominate. So over somewhere to the right, the fields could cancel because the minus q is making a field that goes towards it, and the plus 2q way over there is going to make a field that goes away from it. All right, and those cancel. All right, so then what would the algebra look like and how would it be different? Well, I won't work all the algebra out, but I will analyze the situation and then leave it as an exercise to you if you want to set it up. So if, again, the separation between the charges is d, and we call the distance from the minus q to that point x, our algebra would only be ever so slightly different. If I could revise this that I wrote right here, you would see it would be kq over x squared still for the negative q, so that'd be all good. And then for the 2kq over d minus x, well, instead of it being d minus x, you can see that distance is the sum, so d plus x. That'd be it. So you get a different final answer. All right, and the algebra would go ever so slightly differently, but really almost the same question. You just have to make sure you're solving for, in this case, a spot that is outside of the system of two charges. Now, when you're trying to find a point where the potentials cancel out, it's really not that much different from finding a point where the electric fields cancel out, except that you don't have to mess around with directions at all, because if you recall, potential is a scalar quantity. Right? The formula for potential being, kq over r, you don't need to worry about directions for these things. It's just if it's a positive charge, it makes a positive potential. If it's a negative charge, it makes a negative potential. And so if you have, a plus, plus 2q and a minus q there, the potentials due to the plus 2q are going to be positive, everywhere. It's going to contribute some sort of positive potential at any point you want to look at. And the negative q is going to contribute a negative potential anywhere that you want to look at. So, if I said calculate the potential right there or something, right? At that point, you could plug in this r, you could plug in that r, you could plug in the values of those two charges into your formula, sum of kq over r, and come up with a value. Well, all right, if you're asked to not find the potential at a specific point, but rather find the point where the potential is 0, it's sort of the same exercise as finding a spot where the electric field is 0, but the math will look different, and instead of there only being one valid solution, there are two valid solutions. All right, the reason there's two valid solutions is because it's not a vector, it's a scalar. So when we had two opposite charges, and we did electric field, we said electric field can't cancel in between them because the fields point the same direction. But potential is a scalar. So that means that we could have a point in between them, closer to the minus q, farther from the plus 2q, where the potentials could cancel. Because it's not a question of direction, it's only a question of magnitude. Okay, so somewhere in between them, the potentials could cancel out. Also, the potential could cancel somewhere over here. All right, I picked over there because just like when we did with electric fields, you have to be looking at a point that's closer to the smaller charge because the potential can't cancel out to 0 over there closer to the larger, more positive charge. You've got to be closer to the smaller one in order for it to cancel out. All right, but there's going to be two such spots. So point number 1, oh, actually, we'll discuss in a little bit. There's really actually more than 2 points, but those 2 points are the easiest ones to solve for. Okay, so point number 1, let's say that's the one in between them. We would have 2kq over, if the distance between the two charges is d, and we call this distance x, then the 2q is d minus x away from that point. All right, there we are. And then the minus q creates a negative potential because it's a negative charge. And the potential due to that one is kq over x. Okay, and remember the whole premise of this question is they're asking you to find a point where the potential is 0. So we'll set that equal to 0. All right, the algebra for these is a little bit simpler than it is for the electric fields because we don't have to mess around with square roots. And so actually most of the time you'll get nice looking fractions. So we'll get, I'll switch to red, 2kq over d minus x equals kq over x. The factor of kq will cancel out. And so then we'll just have 2 over d minus x equals 1 over x. Cross multiply, and you'll have 2 times x equals d minus x. All right, group your like terms together. So add 1x to both sides. So now it's 3x equals d. Don't forget what you're solving for. You're solving for x, so the solution is d over 3. All right, so that means at 1/3 of the distance from the smaller charge and 2/3 of the total distance from the larger charge, the potentials cancel out. Obviously, this is a particular solution to that particular ratio of charges. If it were a 3q and a minus q, the position would be somewhere else. All right, so that's the point in between them where the potential cancels out. Now we've got to solve for that point over there where the potentials cancel out. X is going to have a different value, and if you want to call it something different, you certainly may. So maybe I'll go back and call this one like x1 or something. Okay, so whatever. This distance is going to be x2. All right. Well, that means that really only one thing in all of the work that I wrote here for the first question would have to change. I would set it up as 2kq over d plus x2. I'll just say d plus x, but it's a different x. All right, minus kq over x equals 0. All right, so the process is exactly the same. When I solve for x, in this case, I believe the answer comes out to be just x equals d. Again, that's a particular solution. But you can see the process is very similar to what you did for electric fields, but the algebra is easier because it doesn't involve taking the square root. Okay, so I hope that clarifies everything on that homework problem. Thanks, guys.